Now that we have some understanding for how voltages can be generated across the cellular membrane, we're going to talk in detail about how excitable tissues work. And we're going to start with a focus on neurons, and in particular, the part of a neuron called the axon. And the axon we're going to consider in so much detail that it's going to span 2 of these mini lectures. Okay, so excitable tissues transmit electrical current. And we're going to first consider nervous tissue, that is neurons, and then we'll get into muscles and how they work. Okay, neurons are nervous cells, and they have 2 major regions, and those regions can be differentiated by how they function. So this is a cartoon schematic of a neuron, but it is representative of the morphology or the shape of real cells, and that is you have these parts of the membrane that project out into different regions of the body. They could be projecting into other nervous tissue or projecting into, say, epithelial tissue. And those projections serve to receive signals. They can be receiving signals from sensory organs or other neurons. And the signals that are received by the dendrites may or may not result in a signal transmission along an axon. And an axon can branch as well, but here we see it as just a single projection of the cell. And the axon functions to transmit signals. Okay, and it does it in some very interesting ways. And to understand these ways that it transmits signals, we want to focus on the membrane properties of the axon. All right, so what is so special about an axon? Well, there are 3 properties I want to talk about. First of all, it transmits electrical signals. Okay, so what we've seen so far with regards to excitable tissues is that you can have a voltage across the membrane and that voltage can change. All right, so we're going to extend that to consider how the changes in voltage along the membrane of an axon serve to transmit signals. Now it does that only in one direction, at least in vertebrates. Invertebrates are another story. In one direction, it will transmit these signals, and it will do it really fast. Okay, so in this mini lecture, we're going to focus just on the first property, this ability to transmit electrical signals, and we're posing the question, how? How is it the axon transmits electrical signals? In the next lecture, we'll consider the other 2 properties, the unidirectional property and the speed at which it does that transmission. All right, so let's focus in on a single neuron, and we're going to pose this question: how does the axon transmit electrical signals? And we've seen the membrane potential in a prior lecture. We're just doing that right here. We're going to take a recording of the voltage across the membrane, and in particular, our recording electrode is focused on the axon. Okay, our microelectrode there has impaled the axon, and that's going to allow us to monitor the voltage right at that spot relative to the interstitial fluid around the cell. Okay, that's the reference electrode, and so a comparison between our 2 electrodes is what we get on our voltmeter. And that's what we see on the graph on the right, where we have the membrane potential in millivolts, and we see that at rest, we begin with a value of minus 70 millivolts, a typical resting membrane potential. Now, if you are a neurophysiologist and you sit there and carefully watch your voltmeter, of course, we're doing this all on computers these days, periodically, the voltage is going to change, and it does it in a very characteristic fashion. First, you have this slight increase in voltage, and then you get a really rapid change, okay? A very pronounced change in slope, a very steep slope. It rises up to a positive membrane potential, and then it returns back down to where it started. All right, this is known as an action potential. Action potentials have some interesting properties. First of all, they're all or none. Either the axon is generating an action potential or it's at the resting membrane potential. Nothing in between. Another thing is the time scale. Okay, so I've added numbers on the x-axis here, and you can see that the action potential completes all of its changes in membrane potential over the course of 4 milliseconds. That's really fast. Okay, a millisecond is 1/1000th of a second, so you've got 4 of those. Now, also associated with action potentials, or I should say, these are general terms that we use, not just for action potentials, but all changes in membrane potential. There's a certain jargon that we're going to use because we're going to talk in so much detail about how action potentials and other changes in membrane potential occur. And so those terms are as follows. So if you go to an increasing membrane potential from your resting membrane potential, then you say that it's depolarized. Let me get rid of that magnification. Okay, so depolarized is the term that you use as you're going up along an action potential, or really any increase even before we begin that very rapid rise. That's a depolarization there as well. Okay, so any increase in voltage above the membrane potential of minus 70 millivolts is a depolarization. Then as we return back to the membrane potential, we're repolarizing the membrane. If we undershoot it, which is characteristic of action potentials, then we're in a situation where we have a more negative membrane potential than the resting membrane potential. And the term we use for that situation is called hyperpolarizing the membrane. Okay, depolarize, repolarize, and hyperpolarize. Those are terms that I'm going to use. All right, so we've noticed this very rapid change, this rapid depolarization, repolarization, and hyperpolarization. What is it driven by? Okay, so in the last lecture we talked about the Goldman equation, and we described how changes in membrane permeability can cause a change in the membrane potential. And in particular, we focused on the role of sodium. And that's in fact what we see if we were to monitor the permeability to sodium in our axon. So over here, if we took a look at how the flux of ions across this membrane, then we would notice that correlated with these changes in membrane potential are rapid changes in permeability. Okay, so that's what we see in the graph up above in red, is the permeability of the membrane at that spot to sodium. Okay, I'll try to remember back. What does it mean if you increase the permeability? Well, that means, according to the Goldman equation, that the membrane potential is going to approach the equilibrium potential for that ion. So in this case, we would calculate the equilibrium potential for sodium using the Nernst equation. And that would show us that the equilibrium potential is plus 60 millivolts, which is what I've added to the graph there. I've also added this threshold value because we also notice that there was this, or we noticed that there was this change in the slope, and that occurred right at minus 55 millivolts. Okay, so we'll talk about that later, but that's characteristic of action potentials as well. All right, so when the permeability goes up, then the membrane is going to approach the equilibrium potential for the ion, in this case sodium, that has its high permeability. And then when it repolarizes, we have a decline in that permeability. All right, we'll talk about that decline later. First, let's focus on the depolarization part of it. All right, so what drives this change in permeability? Now, I mentioned at the end of the last lecture that gated channels are a means of changing the permeability of a membrane to a particular ion. And among the 3 different types of gated channels, there are voltage gated channels. So a change in the membrane potential itself changes the state of the gate, which in turn changes the permeability of the membrane to sodium. Okay, let me be more specific. Here we're going to focus on the membrane, and what we'll notice in the axon is that there are many, many voltage-gated sodium channels. These are the mechanism for the rapid change in permeability that drives an action potential. Okay, now if you'll recall, on the outside of the cell of an excitable tissue, there's a high concentration of sodium. Now, let's march through time. So first we begin at the resting membrane potential. And at this point, we have a region of this transmembrane protein, the voltage-gated channel, that occludes or blocks the permeability of sodium. And that's the way that it's shown schematically here as a little door. But in reality, it's a region of a protein that blocks sodium flux across the membrane. All right, that region is called an activation gate. And that is the region that opens up provided the membrane reaches threshold, okay, or exceeds threshold. So if the membrane goes above minus 55 millivolts, now if we look on the left, we see the activation gate will open. And as soon as it opens, the sodium will be driven down its chemical concentration gradient and move across the membrane, like that. Okay, so those actions for a large population of voltage-gated channels explain the rapid depolarization that occurs by the membrane during an action potential. Now, there's another region of this voltage-gated sodium channel that is another kind of gate, and this is called the inactivation gate. The inactivation gate is triggered to close by the membrane potential. Okay, so as the membrane becomes very depolarized, the inactivation gate is sensitive to that. And in response to that depolarization, and we're going to march forward on the graph, so now we're in the region where we have a decline in sodium permeability. What happens at the inactivation gate is that it will swing shut. Okay, so that shuts down the permeability. Now, for any particular single voltage-gated channel, it's either open or closed. It has two states. I mean, well, more than two states, because you have the sort of resting state where the activation gate is closed, the inactivation gate is open. But the permeability, as soon as the activation gate opens, will jump. And then the inactivation gate will then close it. That's the third state. And then we'll just have the permeability go to nothing. Okay, so that's the case for one channel. It's just a step function. Whereas if we look at the whole membrane, the permeability has this really gradual rise and then a gradual fall. And the reason for that is that just imagine that there are thousands of these guys all turning on and off, and not exactly at the same time. And as a consequence of their differences in timing, you end up getting a smooth curve for the whole population. Okay, so here we're focused on what maybe the average channel is doing. That is, its inactivation gate is closed. But just bear in mind that there's a large population, and some of them are still open, and some maybe are beginning to reset as well. Okay, so the inactivation gate drives this decline in membrane permeability to sodium. Okay. Now, you might think that that's the end of the story, that basically the depolarization is driven by increase in sodium permeability, and then the repolarization would be a decline driven by a decline in sodium permeability. That is actually not the full story. The repolarization is very rapid, and if it were driven purely by sodium, it would be slower. Instead, potassium will play a role. Okay, now recall, potassium has a really negative equilibrium potential. I'm going to add that to the graph right here, where it's at around minus 90 millivolts. That's the equilibrium potential for potassium. And recall that at rest, the membrane is more permeable to potassium. On the graph up above, by the way, these are not, I've normalized the permeability. So even though the potassium is like shown slightly higher, in reality at rest it's 40 times higher. So this isn't all drawn exactly to scale. But I did that so that we could look at the time course of permeability for the two ions. At any rate, potassium has a very negative equilibrium potential. So if the membrane becomes even more permeable to potassium, that's going to tend to drive the membrane potential towards that very negative equilibrium potential for potassium. So the fact that sodium permeability declines is helpful, but the repolarization is driven by potassium permeability. What affects the potassium permeability? Well, it's another voltage-gated channel. So we focus in on the membrane here, and we see that guy. Okay. Now, potassium is at higher concentration on the interior of the cell. We have that high concentration there. The voltage-gated channel has, just like the sodium voltage-gated channel, a region known as the activation gate. It has the same threshold as the sodium voltage-gated channel. And you'll see over here that there's a rise, a coincident rise for the permeability of the two ions. But notice that the potassium is slower in its rise. And it's because it's slow that it has a delayed effect on the membrane. So while the sodium permeability is surging, it drives the depolarization. But then later on, the slow potassium channels eventually catch up, and that delay allows it to then play a role in the repolarization. Okay, so the repolarization is driven primarily by this potassium permeability. Okay, so if we march through time, we're at rest here. We have the activation gate closed. Same would be true for sodium. But as we move through time, we're now in a situation in time here where the potassium permeability is quite high. So that means that this activation gate is going to be open, and that indeed is what happens. Then the potassium moves down its chemical concentration gradient, and that's why we get the repolarization. Okay. So if we go later in time, then what we find is the activation gate will again close, and that will drive this drop in permeability for potassium. Okay, so the sodium already went through that process. We had the inactivation gate closing the sodium channels. The potassium essentially does the same thing, but just later in time. And note that that drop in permeability for potassium is driven by a closure of the activation gate. There is no inactivation gate for the potassium voltage-gated channel. And just to reiterate, the repolarization is driven by potassium permeability. Okay, so the question that we're interested in with this mini lecture is, what is so special about an axon? And in particular, how is it capable of transmitting electrical signals? We see that it does that through the generation of these action potentials, which are these all or none signals that are driven by voltage-gated channels for both sodium and potassium.